The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Good morning, good afternoon, and welcome to today's webinar, Electric Power Systems Challenges with High Renewable Penetration, Experience and Perspectives from CESI and EnerNex. I'm Carrie Owens with EnerNex, and I'll be the moderator for our session. Before we get started, please know you have the opportunity to submit text questions to today's presenters by typing them into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them there at the end during our Q&A. Once this webinar concludes, all attendees will receive a follow-up email within 24 hours with a link to access the slides and a recording of today's webinar. And with that, I would now like to introduce our speakers. We have Bob Zavadil on the line, Chief Operating Officer with EnerNex, and Bruno Cova, Systems Planning Project Director with CESI. To get us started, I'll turn the mic over to Bob Zavadil.
Thanks, Carrie. Good morning, folks. Thanks for joining us. Just in the way of introduction, why EnerNex and CESI. Some of you may have heard of EnerNex over the years, folks in the U.S. anyway. About a year ago, CESI acquired a controlling interest in EnerNex, actually almost exactly a year ago, because of the synergies between our companies and the fact that our business, EnerNex business, focused in the U.S. and CESI's business focused elsewhere. So we thought teaming up might make good sense. This particular topic is one where we do have a lot of synergies. EnerNex has been involved over the last 15 years in a lot of the renewable integration studies in the United States, North America, as you can see from this map. Concurrently with that, CESI has been involved in assessing renewable integration issues globally, but especially in Europe and Africa. Bruno, do you have any comment to make about the CESI global experience?
Yeah, here you can see just in a very summarized way the record of our main studies the last decade. As you can see, we have carried out studies across Europe, the Middle East, Africa, including Sub-Saharan Africa, and there is no solution fitting all. So each system has its own specific characteristics. Isolated system like Crete, weakly interconnected system like Ireland, stretched system like Italy, and system with different generation mix. So each study has to be tailored to the specific characteristic of the systems, and you will see later the main problem to be addressed.
Yeah, thank you, Bruno. So why is this happening? Back when it first started, it was primarily speculative. People felt that there was a decent chance that we would see a lot of renewables. I don't know that anybody back then we'd be in the situation we are now, both in the U.S. and internationally. Right now, we have 90 gigawatts plus of bulk generation in the ground, all over the country, but not distributed uniformly, of course. Solar has come really quickly. And a little bit later than the bulk wind. And so now we're 60 gigawatts and growing very quickly. The surprising thing about this slide to me is that going back 10 years ago, I would have never foreseen how much bulk system connected solar we have. Obviously, folks are very aware of the distributed solar, both commercial and residential, but just the bulk solar quantities that we're seeing is not lost on those folks that are charged with operating the bulk power system. So why is this happening? A lot of reasons, the old reasons, the concern about carbon and all that. What's really driving it now is on the right-hand part of this slide, and it's the core economics. These numbers come from, I think it's the Lazard Energy Advisory. Charlie Smith from ESIG tracks these continually. And you can see that with regard to solar and wind, the variable renewables, we're kind of winning on levelized cost of energy. And then if we look at sort of recent PPA prices, Lawrence Berkeley National Labs puts out a market report every year, and they're able to dig up these numbers. The PPA prices obviously reflect production or investment tax credits, but those numbers are truly astounding. So that's the driver, and that has led to the future being now for certain regions of the country. In the US, we'll see this in Europe, where it's not sort of what are we going to do when this happens, it's what do we do now. We're all familiar with the California situation. The explosive growth of solar has made the duck curve a reality. This has been on Cal ISO's radar for a long time, and the current situation is that they're exceeding what they projected some years ago with regard to the belly of the duck curve, which is a major operational problem. So it's a reality for some right now, and it will that will be the case for others going forward, most likely. So Bruno, give us a little overview of the situation in Europe.
Similar trends are being witnessed in Europe. Let me recall some key figures of this interconnected power system, one of the strongest in the world, with a consumption exceeding 3,300 terawatt-hour. But let me draw your attention to the cross-border exchange that are nearly 500 terawatt-hour, which means 14% of the consumption. And we expect that this cross-border exchange will grow in the future to transfer surplus of generation, like renewable generation in some area, to the load center. As for transmission asset, you can see here in the box the growing importance of cable technology also for transmission, and notably DC cable. DC technology is, I would say, booming across Europe to interconnect the various areas, also through submarine cables. If you focus on the generation mix, next slide, honestly, we have to recognize that Europe, in Europe, generation is still largely based on fossil generation, namely natural gas, more than 40% of natural gas, and part of the also coal. But thermal generation in general is declining, both fossil and nuclear generation, as you can see on the bottom left, whereas we are seeing a robust growth from variable renewable generation, particularly wind, but also solar. Consider that hydro resources across Europe are almost all depleted. If we focus more on the situation among the various member states, you can see the situation is largely fragmented, with countries that are highly decarbonized, the Nordic countries, the Alpine countries like Switzerland, Austria, but also Latvia, because these countries are relying on hydro resources. So if we look forward now, the evolution is to grow for the renewable penetration, but considering deployment of wind and solar. So the next slide, you can see what is waiting for us. So in the upper part of the slide, I sum it up in a nutshell. The political decision, and here the political driver is a key driver in order to decarbonize the economy in general, not only the power system, with binding target already set, as some of you already know, by 2020, 2030, and we are aiming at a dramatic cut in CO2 emission, minus 90% of emission compared to 1990 level by 2050. This means that in the power sector in 3 decades or so should be almost fully decarbonized. This is not only theory or a political decision, but these decisions are transferred to practical plans. You can see in the table here at the bottom the outcome of the last 10-year National Development Plan formulated by ENTSO-e, the association of the 43 European transmission operators, where you can see an amazing evolution in RES penetration from current situation 35% compared to consumption to a bandwidth between 48 and 58% in 10 years, up to 80% in 20 years, with a corresponding dramatic cut in CO2 emissions. This looks, okay, this is a future, but the future, as already said before by Bob, is coming soon. So let's consider as an example Italy. Situation now is, as for renewable penetration, is 34%, moderate, but already now there are operating hours where load is covered by more than 80% by renewables. And you can imagine a system stretched, more or less it's like Florida, but it's bigger than Florida, from the Alps to Sicily. This system has a length exceeding 1,000 miles, 1,600 kilometers, and the system should be stable also when supplying power with more than 80% of renewables. So challenges are already on the table now. Bob can now give an overview of the challenges, and the aim of this presentation is also to give the solution to address these potential problems, transforming them into opportunity as far as possible. Next slide, Bob, you can give it this.
We'll do that. Bruno, you might be optimistic talking about solution, but we'll try to go there anyway. So, you know, from a sort of a power system engineering perspective and then beyond, when you think about the challenges posed by variable renewable generation, and we need to keep in mind, because obviously we've dealt with hydro for a very long time, and that's renewable generation, but it's much more conventional. It lacks some attributes of the variable part, because the variability of hydro might be over years or decades, whereas with wind and solar, we're talking about minutes, seconds, hours, and you know, out to the decades if you think about the climate change and those sorts of things. So you can come up with categories to contain the various challenges that are posed by these resources. Some of them are system-wide, that you know really involve how we operate the system hour to hour, even year to year. Others are network impacts that are maybe, I'd like to say, as a technical person, volts and bars issues associated with these resources. Across the world, we lay on top of those categories sort of markets, which is the organizing principle by which we operate power systems in many parts of the world. And there we're faced with the fact that we're not dealing with variable cost generation. I mean, the marginal cost of the renewable generation is zero. So that's different than almost anything we've dealt with before. Even in terms of hydro, you can sort of monetize that water and think of it as fuel. So that creates some distortions and upsets in markets already. And going forward, it potentially calls into question whether the markets are defined correctly when we end up with zero marginal cost energy and then potentially variable capacity that we need to deploy for reliability. That feeds certainly into the regulatory overlays and the environmental questions, but we're not going to talk too much about that in this presentation. So we'll start in Italy and a little bit of the historical view of where they've come from today and might look going forward. So I'll turn it back over to Bill.
Yeah, so mentioned network impact. This is one of the first impacts caused by renewable generation, and sometimes it is good to learn from what happened in the past in other areas. You can see here the history of wind generation deployment in the country. Wind is basically all concentrated in the far south and islands, whereas the load is in the center and in the north. And you start at the beginning when installing wind farms. More than 10% of generation was curtailed. So what should not happen is that the investors are connecting new power plants and system operator curtail their energy because of a number of reasons: congestion at a high voltage network, even extra voltage network in the far south, balancing problem in the southern area. So the system operator here reacted, was just a feedback with a solution to cluster wind farm connection into some hubs, solving local congestions, enabling power flows going to the center and north through installation of phase shifter transformer and so on. And now, despite remarkable growth in wind, more than 15 terawatt-hour, in some years 17 terawatt-hours of production, the curtailment is a physiological 1%. So one should, this is a message to anticipate, so one should anticipate the problem and find a solution, consider lead time to construct new network assets or to arrange new solutions. Next slide. If we move to system-wide impact, okay, network can do its good job in fostering renewable integration, but in some situation we have the system that needs to be in situation of crisis. I took here an example of a typical weekend in spring when you have in the upper cube the real load, pretty low for the country in spring. The net load, residual load, that is the real load minus the variable generation, and considering some master units to stabilize the system, we have hours where we have an excess of generation compared to the residual load, the green area. Despite the action of hydro pumping, the blue area, we have an excess of generation. Here, the grid can do little to balance the system, and the system operator has to struggle to either curtail energy or export energy if possible. This is impacted at the system-wide level. Corresponding, we have in these some hours, you can see on the right, as mentioned before by Bob, hours where the energy price is null. This doesn't mean that energy has no value, but simply it's a distortion, a distorted signal of a market price. The value of energy here is transferred to the ancillary service market or the capacity market. So one has also to design in an appropriate way the sequence of power markets in order to give the right signals to the producers and also the consumer on the other side. So this is just an overview saying that we have in the next slide need of solution related to the grid, related to the system as a whole. You can see on the bottom left, simulation applied to the year 2030, referring to the national energy strategy. In this case, we have hours where the residual load that is negative. So we need storage. Otherwise we have to curtail the surplus of energy. So surplus of energy followed by need of a steep ramping, more than 10 gigawatt per hour for a few hours to catch up with the load in the early evening. So here again we have to find solution providing higher system flexibility. On the one side storage, but also I underline other solutions, change operation paradigms, demand response, others. And also storage, okay, hydro pumping when possible, very rarely nowadays. So utility scale batteries, but also let me underline cluster of electric vehicles. Electric vehicles sometimes are seen as a threat for the system because they add spikes potentially of power tapped by the system. It's actually electric vehicle could be seen as an outstanding resource for system flexibility. and this should be really targeted, addressed as a potential opportunity, not as a threat to the system, and other non-conventional devices that we might recall later. So this is just to give an overview on the multiple impact of renewable in the system, and consequently multiple solutions to address this impact. So moving on.
So thus far, we've really talked about energy in terms of how much and where it's produced and where it's sunk. We need to keep in mind that the real goal here is to ensure the security of the electric power system. So there are a lot of other things going on underneath the hood, rather than kind of these overview market economics. And the other issue is that we can't just do this pretty good. We've got to do it at least as well as we have in the past. So it really introduces this concept of flexibility. Flexibility not only to deal with sort of the gross energy, transport issues, but to simultaneously guarantee the security of the system, or ensure the security of the system against whatever metrics we plan. So there's measures that we've been employing for some time that, in the early days at low penetrations, we're really just redispatching or changing how we use the conventional units. Building transmission to reinforce the network has been recognized as a tool in the RTOs in the US and certainly in Europe and elsewhere. And then as renewable penetrations have grown, we are forced or motivated to look for additional measures for flexibility. And Bruno talked about storage. There are others that are somewhat non-capital that we've already learned to use. And a lot of those had to do with changing the rules by which we operate the system. But the point is, this is a sort of an exhaustive view in terms of making sure that the tail events and the extreme conditions are appropriately evaluated and considered in our planning analysis. And Bruno's going to talk a little bit about some of the approaches the approach they've been using for some of the studies in Europe.
Yes, so as Bob said, we have to quantify and appropriately evaluate some indicators in order to be able to take decisions, and also to assess benefits when taking some investments on the system. And so let me underline system, not only the grid. Here, what we have developed are computational tools based on probabilistic simulations. So here, it's not sufficient any longer to take snapshots or extreme operating conditions like it used to be in the past. We have to scan all the expected condition over a whole year and examine all probable system operation conditions. We have developed a tool, a grid reliability and adequacy risk evaluator, widely used in Italy by our system operator in other European countries. So in appendix, when you will download the presentation, we have more details. Basically, we simulate the system hour by hour over the whole year through the Monte Carlo probability method, randomly drawing possible system configuration, tens or thousands system configurations, taking into account unavailability rates of generating units, line transformers, the action by the system operator, but also the variability for the intermittence of wind and solar generation, combined with the forecast error of power demand. So we have to combine this additional uncertainty in order to evaluate how the system can react to supply load to the residual, supply power to the residual load. So this modeling can be applied to practical example. Here, I took an example taken from Algeria, a study we did for Algeria, midterm 2025. This just to underline that it's not only the US or Europe that are moving towards decarbonizing their power system, but also Arab countries or sub-Saharan African countries. You can see here that if we operate Algeria isolated, especially in spring and autumn, we can face a substantial amount of renewable generation curtailment. Same generation mix, but it's opening up the borders towards Morocco and Tunisia, so simulating in a coherent way the whole interconnected Maghreb. We can see how the rest generation curtailment drops, so is almost zero when you exploit the full net transfer capacity at the border, always keeping N-1 security criterion. So here you can see, for instance, the key role of interconnection in helping a better exploitation of renewables. Of course, this means that during our modeling and simulation, we have to model and simulate the whole interconnected system, in this case, the whole Maghreb. In Europe, normally we used to simulate the whole pan-European market and model to take into consideration the interrelation between the surplus in one area and shortfall in other areas, or the opposite. And this is an example, just a visual example for you to have a flavor of what should be done to find some possible solution of operating way of interconnected power system.
Yeah.
So in the US, please, Bob, you can say more.
Yeah, well, just a little bit more. I mean, we've learned a lot in the last 15 years because this is actually happening. And as I mentioned previously, some folks have been, don't want to say battling, but have been seeing and responding and developing approaches to ease the integration of more variable renewables. And we've learned, at least at a higher level, about the mechanisms and the tools we have at our disposal. Bruno mentioned interconnections, and transmission is certainly one, but in the US, we're somewhat balkanized with regard to the large-scale transmission that I think they have a little bit more, what would you say, push for in ENTSO-e and in the EU countries. But there are other measures that potentially don't involve large capital investments. We've used the makeup of generation fleet is important, but we've seen kind of a movement to natural gas, which for electric generation represents a very flexible resource. But now we're seeing enough renewables in some places where the question comes the gas supply, and so we consider that. Obviously, grid modernization and smart grid, the fact that demand may actually be a resource in the future is coming before, as opposed to this hard constraint that it can't be changed, from the operational sort of level. With regard to system control and markets, we've learned that large operating footprints make a lot of difference in terms of the sheer number and maybe variety of resources that you have to control. And it also takes advantage of the geographic and spatial diversity that you see with variable renewables, and that there's some smoothing of aggregate production over those large footprints. So, up till now, it's been recognized that storage is one of those tools for increasing flexibility. And I think we've proceeded for the last 15 years on the notion that storage was really expensive, but we seem to be close to a tipping point, as proven by some commercial projects where storage is close to being in the money, and we'll have to consider it, I think, more strongly going forward as the magnitude of renewables that are under consideration increases. So there's kind of a second level of issues we talked about in terms of integration. In the United States, the American Electric Reliability Corporation is the ERO for the US under FERC, and they don't care about markets too much. They don't care about flexibility per se. What they're about is reliability. And they launched a task force. Actually, this was a follow-on from an activity that began in 2007 to really sort of assess variable renewable generation and potential impacts on the system. The Essential Reliability Services Task Force picked up from there in 2014 and started to take a really close look at reliability risks from the changing generation fleet. Changing generation fleet being coal going down, renewables going up, and probably more gas. And in this task force, they identified the crucial aspects or attributes for maintaining reliability as being the frequency support, being able to control voltage, and then being able to balance the system. And the determination was that all new resources must be able to support voltage and frequency. They recognize that with growing distributed generation, that the standards that govern how that equipment is designed and how it operates need to be in sync with needs from the bulk system. So a harmonization between IEEE 1547 and the NERC reliability standards rose up to near the top of the list because of the amount of DER that's in the ground. And then a concern about all this DER that can't be observed from the bulk system level, say in real time or hours ahead, as being something that must be examined further because it poses several threats to the balancing and the real-time reliability concern. So we dig down into some juicy technical topics. NERC also recognized that one of the attributes of the variable renewable generation was that it was, as they call IBR, an inverter-based resource that has much different technical attributes than the more familiar conventional generation. So I'm going to turn over to Bruno to talk about the inertia issue a bit.
Yeah, you can see here in a visual way the transformation from the classical rotating masses in conventional generation to asynchronous generation. And this means that facing the same level of disturbances, the same gravity of disturbances, frequency deviations are becoming higher. And this is not just an academic scheme or graphs. If we move to the next slides, you can see what happened across Europe in the last 15 years, 20 years. I said before that Europe is the European interconnectivity is one of the strongest in the world. In spite of that, in the last 15 years, the frequency deviation, the number of events of frequency deviation exceeding 75, 100 millihertz have become more frequent. The system basically is lighter, has a lower inertia. In the last years, the system operator retrofitted, reacted, and so frequency deviation now are not increasing any longer like before, but this is one of the effects in replacing conventional generation with the photovoltaics or the wind farms. So in the future, we are saying that we are aiming to decarbonize the system, deploying increasing amount of photovoltaics and wind. And so we don't want to end up in unstable system, not able to cope with any disturbances simply because there is no inertia. There are solutions for the future or the near future, summarized here on the right side of these slides. Bob can say more because some of the solutions are related to the US.
Well, just a bit more. Obviously, this concern is driven by variable renewables, but the evolution of the technologies that we use for wind and solar plants does provide, maybe part of the solution and maybe a bigger part going forward. With regard to voltage control, static, dynamic, reactive power support, we've learned to build renewable plants so they behave pretty much like conventional plants. in terms of being able to dispatch reactive power and grow voltage, both in the steady state as well as disturbances. For some time, for example, in ERCOT, we've recognized that the frequency response from renewables is there, especially in the down direction. So if they lose a large block load and system frequency goes up outside of bands, that renewables are very nimble at reducing generation, probably more nimble than conventional plants. To do that in the other direction, if we were to lose a chunk of generation, renewable plants would have to be pre-curtailed, and there's an economic cost. But the technical capability is certainly there. Hydro-Quebec, over 10 years ago, maybe more than that, required a kind of a synthetic inertial response from wind plants, which is also possible, and you can get some short-term support without having to be pre-curtailed. If you want actual kind of synthetic governor response, again, you would have to be spilling energy waiting for that event. So the OEMs on the wind side and the solar side are aware of the requirements and aware of the capabilities at their disposal, and are watching this very closely as the grid connection requirements evolve. I will say, however, that the wind folks have been dealing with this for 2 decades. The fact that solar has kind of exploded on the scene in the last decade, maybe less than that, there are some issues, and for your reading pleasure, I'd reference the NERC report on the Blue Cut disturbance back a couple of years ago as some interesting reading with regard to, we don't quite have this completely done yet. Now, with regard to voltage, reactive power management, we can do that, but our attributes of variable renewable generation that we can't overcome, and it's really their ability to attribute short circuit current to a system fault. And Bruno described, one of the kind of underneath the hood issues that we haven't quite figured out how to address yet.
Just to be brief and to avoid overrunning at the time, I guess one picture says more than 1,000 words. So you can see here an example of a short circuit simulated in around Naples, the southern part, with all conventional generation running, and voltage dip for the short circuit is limited to a relatively small area. When we are installing more and more wind and photovoltaics in the south, the same disturbance, the same short circuit would affect a much larger area, with consequent potential problem of bad intervention of protection, cascading effect, a potential risk of cascading effect of units that might disconnect on a wider area. So this is one of the aspects that should be addressed, as mentioned before by Bob, together with the inertia. So they are basically interrelated. Poor inertia is also poor short circuit power, and so these are the effects. So need for going forward, and some ideas are here summed up, and Bob can comment more.
Yeah, I will a little bit. I mean, from where Bruno and I sit as power system engineers, when we think about the future, one of the things that stands out, and we're already seeing it, is that power systems are becoming more complex. We have devices and systems that we haven't dealt with before, and so we're talking about the technologies used in variable renewable generation. We've got these coming changes on the demand side where load isn't just load anymore. It might actually, be able to respond to bulk system disturbances in ways that we currently don't understand or maybe can't even imagine. And on the demand side, things might be changing very substantially, especially with electric transportation. To me, that's kind of almost a game changer. We haven't been in a mode where we've seen growing demand in energy on the load side. Electric vehicles would certainly change that. It's going to have an effect on the distribution system, but in the aggregate, certainly at the bulk system level. And then, as Bruno mentioned before, there may be opportunity if we employ them or deploy them correctly to actually be a contributor to bulk system reliability. So need to increase or up our game with regard to our ability to analyze, plan, and even adapt how we've done things for many decades to keep pace with this system as it changes and to stay ahead of the curve. We are already running into certain limitations with regard to our present engineering practice. The tools we use, for example, for bulk system analysis being, positive sequence only, RMS based, can, in certain circumstances, kind of hide maybe some of the issues that we would actually experience in the field. And so we had to sort of rethink how we analyze those problems, keeping abreast of new technologies and the appropriate models that we use for study is going to be a growing challenge, actually. And then, we've done pretty well over 100 years with planning sort of generation, transmission, and distribution separately, with growing DER, with grid modernization and smart grid and those sorts of things. It sort of calls into question whether that compartmentalization of those planning and analysis functions will be what we need in the future. So we're going to talk just briefly here. We're running close to time on kind of a summary, but specific opportunity solutions that we see in some various areas, and then we'll wrap up. So I'll turn it over to you, Bruno.
Yeah, just we said it's integrating renewable generation into a system, the power system, is like solving a puzzle. On the upper right here, there are then consequently multiple solutions, mix of solutions. For sure, transmission system can play a role. I mentioned the example of interconnections, the example of Algeris I recalled before, but here you can see some amazing number of investment estimated by European transmission system operator in 10 years, more than 110 billion euro in infrastructure of European relevance. The largest share of this investment are justified namely by renewable integration, but it's not only the grid, it's a line, circuits, but also VAR compensation equipment. We mentioned the problem of voltage support and inertia, synchronous compensator. Synchronous compensator looks like a solution of the past century, but it's not that. In Germany, in Italy, and so on, quite a lot of new synchronous compensators now are being installed to cope with the problem of inertia. Market, I mentioned the problem, the issue of market distortion. We come back here perhaps in the question and answer. Here we have to properly design the market model and markets model, plural, so from the ancillary to the capacity market, take into account potential new sources, virtual power plant, electric vehicle, as mentioned before, and introduction of new product. Other possible solution, we mentioned flexibility, the next slide. Flexibility is not only storage by itself, but other non-conventional solutions. Let me recall power to gas. In Germany, more than one pilot plant has already been started to transform power in an hour of surplus of power to synthetic gas. And gas basically can be then used to generate power when needed. So power to gas is another measure to ensure flexibility besides the electric vehicle, battery, and so on. And finally, digitalization, integration of transmission and distribution through the introduction of a new concept of prosumers, energy community, distributed storage, because renewable, especially solar, has been deployed largely on medium voltage and low voltage level. So perhaps the boundaries between transmission and distribution in the coming years might disappear. Let me use might, but it's what we are already seeing.
So, conclusions, that's a pretty strong word. I know that these are conclusions. There are some observations from direct experience, and folks on the line that have been working this area might have some others. But what we're seeing is that we're moving to higher shares of variable renewable generation, sort of across the globe, and that's driven by economics. We need to adapt to keep up with this. We've already seen some of this in terms of operating practices, markets, sort of even engineering practice in terms of how we deal with this changing power system. And the last couple decades, in my opinion, have demonstrated the industry's ability to adapt. We would do studies 10 years ago looking at large amounts of renewables, or say 20 years ago, and the folks on the operation side weren't all that interested because it wasn't their problem yet. But they started to see it. They worked very hard to adapt and continue to evolve, so that, you know, integrating increasing amount of renewables is part of their day job now. And then going forward in the future, the anticipation is important, because some of the things that Bruno mentioned with regard to things that have been sort of off the radar scope, like power gas as a source of flexibility, you know, those sorts of things are going to be increasingly part of the visioning that we have to do in these kinds of analysis. So I think with that, I'll turn it back to Carrie. One more thing for folks that aren't members of the IEEE Power Energy Society. I would refer you to this biennial issue on renewable integration. There's been 7 of them over the last 15 years. And if you're interested in the copy, it's a pretty good snapshot of where things are at, not only in the US, but globally. The entire issue is devoted to this topic. And if you don't have it or you're interested, you can send us a note and we'll get you one. So with that, I'll turn it to you, Carrie.
Thank you, Bob. And just a reminder for those on the line, we are still accepting questions. So if you'll go to your questions pane and submit, you're welcome to do so. We do have a couple of them that have come in. The first, referring to the probabilistic approach adopted to assess system reliability and RES curtailment probability, how are extreme weather conditions simulated?
So I might answer. So Bob answered this question. So I said, okay, we have to consider a whole year, the operating condition over a whole year. But during the year, we have the same year, we might have different climatic conditions in terms of not only wind or solar, but especially hydro inflows. We might have drought years, more years of more wet. So on the one side, when adopting probabilistic analysis, we apply the so-called climatic years. So based on the recording of the past series of, for instance, hydro inflows, wind regimes in the various years, we simulate this situation, and with the corresponding weight of probability of occurrence. So this is a whole for the whole year, wet, dry, and so on. Within the year, we might have extreme weather conditions like hurricanes or typhoons and so on. So in the random drawing of an availability of transmission or generation assets, we have some time windows when we can simulate either bad weather or extremely bad weather, to take into consideration also what can happen in the system as a risk of load shedding or generation curtailment in this extreme situation. All is weighted with the probability of occurrences. So that's why we were underlying the need for adopting probabilistic approach instead of a deterministic approach like in the past.
Just to add to that, Bruno, to do a probabilistic assessment, you need to have a basis to develop your statistics. And we're in a position now where, records that relate to variable renewable generation have been, accumulated for some time. We're sort of building that basis. On the hydro side, folks deal with hydro have 80+ years of basin water records and stuff, and that's how they do their planning. We're moving in that direction, although we're maybe have only a decade or so with regard to renewable generation. So to identifying the extremes with increasing confidence will be possible now as we move forward. 2 years ago it wasn't, because we simply didn't have records.
Yeah, correct.
Thank you. Next question, just a couple more, we've got some time. With VRES marginal generation costs close to zero, how do you think future markets with very high renewable penetration will be managed?
I'll take a stab at that, because if you look at Hawaii and their stated goal to reach 100% renewable by 2045, it makes you think about if you've got sort of an economic or market kind of organization of that, how it's done. And for me, it really says is that energy has almost no value. It's controllable capacity that needs to be procured in the market. So maybe that's a solar plant that is overbuilt on the DC side with P arrays because of the costs, and they operate in a way that their capacity can be dispatched for the maximum number of hours. So you are really incenting capacity, and as Bruno mentioned, possibly other reliability services, but the energy value is actually going towards those other things. And so in that extreme situation, it's a little easier to think about. The transitional problem is maybe a little more difficult.
Yeah, this is what I already mentioned. The value of energy is transferred to other markets. One is on capacity. These markets that are now growing across Europe, have already been introduced in some European countries. The other is ancillary market that is going to have a bigger value. So units that are flexible to provide ancillary services can have revenues. So when deciding to build a new plant, one should consider the full set of markets, from capacity to the ancillary. And this is what we are simulating. In some cases, investments are more justified from revenues on markets other than the day-ahead market.
Okay.
Thank you. And the last question. We are already seeing a shift of value from day-ahead to real-time markets, and value of ancillary services generally going up. Do you think that this trend will continue?
Well, that's a good question.
Yeah, it's a battle. As I see it from, perhaps Bob, you can say more on the US system, because in Europe, the amount of money and then what the customer should pay for the ancillary services is growing due to the more volatile generation in the system, the need then for ramping up with a higher cost to provide this kind of services. So the market, the ancillary market is growing on the one side. On the other side, the aim of system operators is to warrant the system security and reliability at a minimum cost. So they are reacting, installing some new network assets in order to minimize this. So on the one side, there is a trend pushing up the cost for ancillary markets. On the other side, actions in order to smooth this trend. But the reality is that in the recent year, the ancillary revenues for ancillary markets, revenues for producers, cost for consumers have gone up. So this is what is happening in Europe. But the market model in the US is slightly different.
Yeah. Well, I mean, from the U.S. perspective, if we look at differences between day-ahead and real-time, there are those, traditional, been around forever kinds of things in terms of a unit in day-ahead goes on an outage in the next day, right? So you have difference that you need to respond to, and it potentially can affect cost. With regard to renewables, it's how are they incorporated in your day-ahead processes? What do you think is going to be delivered on an hour-by-hour basis? And then what actually shows up? And so two things that, we've already invested pretty heavily in. One is on the forecasting side. We've gotten a lot better, a lot more sophisticated at forecasting day-ahead renewables. And on the second side, we in certain footprints like MISO, developed actual market mechanisms that try to deal with those differences in the most sort of efficient and transparent way. So rather than taking action that turns out to be really costly, there are smaller adjustments that are maybe anticipated a few hours ahead when the uncertainty is lower that can reduce that impact. So that's an area where it's really interesting to see how the learning feeds into actual practice implementation, and some of those things have worked out very well. As the share of renewables grows, obviously, this will become a big issue and maybe a more difficult one to address, but we'll see.
Thank you. And with that, we'll conclude our Q&A time together. A thank you to all our participants this morning. If you do have questions, feel free to contact EnerNex via our website, www.enernex.com, or email info@enernex.com. Be sure to connect with us on Twitter and LinkedIn as well. After this session, a reminder, you'll receive a follow-up email with a link to access the presentation slides and a recording of today's webinar. On behalf of EnerNex and CESI, thank you for joining us. Have a great rest of your day. And this concludes our session. Thank you.
All right.
Thank you.